Welcome to a lesson with Dr. Powell. Let's take a look at how we can describe what an incidence matrix is and what it represents for a digraph. A digraph is a um, graph with vertices and directed edges. Okay, so the incidence matrix describes a function or linear transformation um, that answers the question, given a collection of edges, what the ultimate net boundary is of those edges. So if I have an edge, say like E3 right here, it comes from V1 and V2. Now, what are the borders of this edge? The borders are like its tail and its tip. Its tip gets a plus value and its tail gets a minus value. So we could say, if we use, so if we have F as being the boundary of the edge E3, we say it's V2 minus V1 because we have tip minus tail. Now, if you had a collection of edges, all right, we could represent this with a plus symbol if we would like. So like E1 plus E4 plus E5, that's a collection of three edges. What's the ultimate boundary of those? Then we could write that out. We could say that this would be equal to, thinking of f as being an additive function, so adding up the individual results, like saying f of E1 plus f of E4 plus f of E5, then this would be equal to, let's see, E1 would be V2 minus V1, because tip and tail, and then plus an E4 would be V3 minus V1 plus V3 minus V1. And then E5, you could think right here, we'd say V4 minus V1. So plus V4 minus V1. So if we add up these, so we add that up, collect the V1s together. So it looks like we have minus 3V1 plus V2 plus V3 plus V4. And that would be the result of this function. Now, if we want to create a matrix which describes what this function is doing on collections, we note that this idea is additive. Okay, at least the way we want to frame the question and answer it is additive. It's an additive function, and there's a way of describing additive and scalable functions. You could use scalars in R if you want to, not just whole numbers. And really, the result will restrict down to exactly what we want here, even though the matrix may do more than what we need. So let's take a look at this and write down what our matrix might be. All right, so let's clear some space here. All right, and see what this is. Now, in order to do this, we're going to use a column interpretation. So we're going to see exactly where does edge 1 go, where does edge 2 go, and so forth. So it looks like these might be basis vectors, right? That's what we're going to be thinking of edges as. So we're going to be thinking of a vector space. E has dimension 9. Okay, so this vector space is going to be like, you could think of it as R9, if you will, if you're thinking about scalars as being reals. So you have a 9-dimensional vector space made up of basis vectors, which are just the edges, and then of course can take any linear combination of them. If we're just looking for collections of edges, though, I suppose then really all we need is just sums of them where the coefficients are 1. So this is a lot more information than we need. However, we can still, the matrix that we build can still describe the function that we desire when we restrict it down to the linear combinations that are important to us. Okay, so we start here at a vector space E. That's our domain. We're taking a collection of vectors and we want to see what the over our boundary is of that collection. Now, to do that, notice that the boundaries are simply made up of vertices, right? So we're going to think about these vertices then as being linearly independent and maybe basis vectors of a vector space V. So that would be R4, since there's 4 of those guys. That's isomorphic to it. So meaning that it's R4. I mean, we have 4 basis vectors here. And let's create a map between this vector space and that vector space. That's what we want. That's what our boundary map is. It describes that. So if we're thinking about this matrix, we can get the size of it. If we're thinking about a column interpretation, since we have 9 things coming in, it looks like we're going to have we're going to have 9 columns, and we're going to have 4 rows because the outputs are going to be in R4 as we go along. So it's going to be a 4 by 9 matrix, 4 rows, 9 columns. Okay, so let's kind of spout out how this is going to go, knowing that the first column is going to give us the image of E1. So the image of E1 is simply going to be, and we're going to think about the output as being like coefficients of V1, V2, V3, and V4. So coefficients of those guys. So the output of E1 is going to be, so the output of E1 is going to end up being just V2 minus V1. So we have, so V2 at the tip, V1 at the tail. Okay, so that's where E1 is going to go to. You can put a 0, 0 here. All right, that's where E1 is going to head to. E1 has a tip there and a tail there, E1. Okay, now where does E2 head? So here we think it looks the exact same. Okay, so we have a -1, 1, and E3 is also the same. Okay, not too bad. Okay, we need 6 more columns here. So we go on to E4. E4 is right here. It looks like V1 is again a tail, and the tip this time is V3. Okay, and then we go to E5. Looks like the tip is V4, and the tail is again V1. Okay, then we go to E6, and it looks like the tip this time is V1. All right, V1 gets to be a tip. And the tail is V3. All right, so that we just did we just did E6. Now we'll do E7, which actually is the same as E6. So we have E7 would be this one right here. Okay, then we go to E8, so the tail is at V4. And the tip is at V3. Then we go to E9 right here. It's a loop. So you think about it, actually, so it's at V4. So V4 gets a -1 and a 1, but they cancel out. So you just get a column of zeros. Okay, so you have E1, E2, image of E3, E4, E5, E6, E7, E8, and E9. And this is the incidence matrix for this particular digraph. Thanks for watching.